Hi, I'm Hana the Best,
And I'm Natalie the Bay.
and today we'll present the concept of nuclear energy as well as the extreme effects of radiation on people in extreme situations.
Like the disasters at Fukushima or Chernobyl. So, yeah, let's get started.
Radioactive decay, noun, the spontaneous breakdown of a nucleus of an atom that results in the emission of matter and energy. These atoms are called radioisotopes and must have unstable nuclei that do not have enough energy to bind the atom together.
Now, when and why does radioactivity occur? And if atoms are supposed to continue decomposing, why is it still going on? Radioactive decay has been going on since the very densest elements were created in the Big Bang. Such heavy nuclei decompose into more stable and favorable compositions over both long and short periods of time. These amounts of time are generally quantified in halves. The half-life of radioactive material is the time it takes for radioactivity of an isotope to fall to half of its original value. Remember this equation?
Now, some elements take seconds to break down, while others take billions of years. In nuclear energy, we generally focus on U-238 and U-235. These isotopes are some of the only radioactive elements that are common on Earth and decompose at a rate that facilitates the production of energy.
In the first reaction, uranium-235 isotopes clash with one neutron to form krypton-93, barium-140, and three more neutrons, as well as heat, which is not shown in the equation.
The second reaction takes U-238 and yields thorium-234 and helium-4, which is more commonly known as the alpha particle.
The latter two reactions are similar to the first reaction, but produce completely different products and different numbers of neutrons.
Thus, there's a chain reaction put in place. Once again, all of these reactions release energy. We can further see the continuation of this chain reaction as the neutrons released by U-235 continue to react with other U-235 isotopes, further releasing heat. So how do we contain so much heat production?
Well, this process of breakdown of U-235 and U-238 nuclei, called fission, produces large amounts of heat which can be harnessed for nuclear power. Energy released heats water containing the radioactive material, whose steam then powers turbines which produce electricity. Control rods, generally made of cadmium and boron, absorb stray neutrons and thereby control the rate of radioactive decay. For less heat, more bars are added, and vice versa for the opposite.
This mode of production of energy produces a lot of power, but also creates a lot of radioactive waste, as the products of U-235 and U-238 reactions will continue decomposing.
For that reason, we still have issues managing radioactive waste, which brings us to the next topic, the effects of radioactivity on people in extreme situations.
In the past 3 decades, there have been 2 accidents in particular that have seriously devastated surrounding populations.
Chernobyl and Fukushima incidents classified a level 7 on the International Nuclear Event Scale, the highest rating possible. The Chernobyl incident was a catastrophic disaster that happened on the 26th of April in 1986, when an unexpected power surge during a systems test ruptured a vessel. Radioactive fallout spread throughout Eastern Europe, the substance most heavily concentrated in Belarus, Russia, and the Ukraine.
In contrast, the Fukushima disaster occurred after a massive earthquake and tsunami on March 11, 2011. The earthquake broke the nuclear reactor cooling system in the plant, and so heat produced by the nuclear reactions continued unmoderated, releasing large amounts of radioactivity into surrounding zones, contaminating water sources.
Another very potentially damaging type of radiation is called gamma decay, where electrons in an unstable excited state are demoted to a lower state and thereby release mass amounts of energy in the form of gamma particles, possibly in the visible light spectrum. These particles have the power to penetrate cell walls, thereby damaging the reproduction of cells and either stopping cancer or causing a hell of a lot of health problems.
Fun fact, radiation therapy uses gamma decay to kill cancerous cells. Yay, saving lives! Chemo, anybody?
Radiation therapy does, however, come with many side effects. Powerful gamma rays penetrate the skin, on many accounts destroying tissue and healthy cells along with cancer cells. Accounts of radiation burns, cataracts, hair loss, ulceration, and even death have followed exposure from Fukushima and Chernobyl.
Radioactive waste in the water and soil accounts for dangerous mutations of both animals and people. Cows graze and produce milk, and babies drink said milk, contaminated with excess amounts of cesium and other radioactive material, causing large irregularities in body development.
To this day, hospitals and orphanages in Belarus and the Ukraine address the cancer research for children of Chernobyl families. That's a 3-generation difference, people. Radiation from both disasters has spread all over the world, and the globe might never recover from these disasters.
We leave you with the concept of stronger and absolutely sustainable energy, fusion. Fusion energy happens when two hydrogen atoms combine to form deuterium, an isotope of hydrogen, and one electron. Deuterium then collides with hydrogen atoms to produce helium and gamma rays. Then the two heliums collide to create an alpha particle, two hydrogens, and another wave of gamma rays.
Although all of these reactions produce enormous amounts of heat and energy, they only happen on stars as it takes incredible amounts of energy to heat up atoms enough to override atomic nuclear repulsion and create new nuclei. But if we could somehow harness the energy,
it would be awesome.
Exactly.
So yeah, this is our video on nuclear energy and its effects. And here are our sources.
Yay!
Yay!